here. This serves as our lecture for section 1.5 for our calculus for business. So we're continuing chapter 1 on differentiation. So here we'll be looking at section 1.5, Leibniz notation and the power and sum difference rules. Some objectives. That edit. For mine here. This serves as our lecture for section 1.5, so we're continuing chapter 1. 1.5 is covering section Leibniz notation and the power and sum difference rules. Some objectives here: we'd like to differentiate using the power or sum difference rule. We like to differentiate a constant or a constant times a function, and we like to determine points at which a tangent line is a specified slope. When y is a function of x, we will also designate the derivative f prime as dy by dx. All right, so whenever we see dy by dx, it's the same as f prime, which is the derivative of y with respect to x. For any real number k, the derivative of x is some power or to some real number k is going to be that k times x to the power of k minus 1. So what this means is when we take a derivative of a power function, basically that power comes down in front, which you see here, and we subtract 1 from the exponent, right? That's right. And so in the past, we were doing the limit definition of the difference quotient, where we would say the limit is h to the 0 of the difference quotient. All of that is condensed down into like stuff like this, all right? So this is one of several shortcuts. Initially, the shortcuts might be information overload, but once you practice them a few times, then they kind of become second nature. Examples where I to differentiate each of the following, right? If we're working on part A, if we have y equals x to the 5th, here, let's start here. The power function, what is going on today? All right. So then the derivative, or we're going to call it dy by dx. This means the derivative of y with respect to x. The exponent comes down, right? And we subtract 1. Right, those are the two things that we're doing. So then this is going to be 5 times x to the power of 4. And like if you wanted to if you feel like you needed to convince yourself, you can do the limit definition of the difference quotient of this. When you simplify, once you take the limit as h tends to 0, you'll get the same result. X, the derivative, or dy by dx, which is going to be what, 1? Because so there's an implied 1 here. So this is x to the power of 1. Again, that 1 comes down and we subtract 1. So then ultimately, we're going to get 1 times x to the power of 0. X to the power of 0 is 1. So ultimately, this is just 1. Equals x to the negative 4. When we take the derivative, or dy by dx, the exponent comes down, so that's going to be a negative 4x. Negative 4 minus 1 is negative 5. Before we got our 1, and we got our 4x to the power of negative 5. Let's see. It's an exercise, right? You have the solutions here. if you need to see those worked out, just let me know and I'll make a video working out those specifically. I'm just gonna kind of stick to the examples right now. We have a lot of sections we're trying to get to. So here we're actually differentiate. So let's start with part A. We have y equals the square root of x, right? So I think so far we've been doing like a power rule. So we have a radical, right? So how can we apply the power rule to this? Well, we can rewrite this radical as a power. So this is going to be the same as x to the power of a half, right? So now when we take the derivative of y with respect to x, all right, that half comes down, and then a half minus 1 is a negative half. All right, I'm going to leave it like this for now. I mean, we could you know, we could exponent as a fraction. I'm just going to leave it like this for now, and we'll adjust. We might need to take it a little bit further, but it's just what we're going to say. And then for part B, equals x to the power of 0.7. So then our derivative of y with respect to x, the 0.7 comes down. 0.7 minus 1 is what? Negative 0.3. Again, those negative exponents, you know, since we're working in Pearson, just kind of follow the instructions, and you have to work a few examples to just make sure you're doing it the right way. I prepared notes. Okay, so they just see, like, for instance, in the first one, we stopped here, right? Then the negative exponent moves it to the denominator, right? And then I guess we should have just gone a little bit further. But then this one, they left it as the negative exponent, right? So like with these, so you get a negative exponent. I mean, you can't really go wrong taking it further. And then something like this, you know, just leave it there. If you submit a question on Pearson and you want to like refute it, like you think it's right, but they and like you want to challenge it, just let me know. I can look at it and I can give you credit for it. Because sometimes you guys do put the right thing and like Pearson doesn't give you credit. That happens every now and then. The constant function is 0, right? Because a constant, all the constants other than 0 can be written in the form of like whatever that constant is times x to the power of 0, right? But the zero function, it's not unique, right? So you can write any constant like this to have a derivative though. Let's kind of look at it. Sometimes a function is the constant times the derivative. Derivatives, right? Oh, I'm still stuck on the 0 thing because there's something there and it'll pop up. Let me put a pin in that. We're gonna have to come back to that notion or idea. So a derivative of a constant is the constant times the function. So this is just a theorem, right? So again, the derivative of a constant times a function, basically it's like that constant can go in front of the derivative. You see it here, right? Each of the following derivatives. So then for part A, differentiate this with respect to x. This 7x to the 4, right? So then that's going to be equal to the pound. So 7 times 4 that ends up being 28, x to the power of 3. What's the constant times the derivative? I can show more. You'll see it in just a moment. For part B, dx of negative 9x. X is just 1, so ultimately this is just going to be negative 9. I'm really just taking the derivative of the variable and then multiplying it by that constant. I'm putting the constant in front, taking the derivative, and then multiplying that. That's essentially what I've done in those two examples. So then for part C, we're actually finding d by dx of 1 over 5x squared, right? So this is going to be the same as d by dx as 1/5 x to the power of negative 2. It can go in front. We can just kind of ignore that for a little bit. The derivative of x to the negative 2. So the negative 2 is going to come down. We're going to have a negative 2/5 x to the negative 3, right? Because you got to subtract 1 from the exponent. But cubed, okay. And then we got negative 9. And that was negative 2/5 x to the negative 3. We just move it to the denominator. Generally, we do write the exponents as a positive, so you want to move it to the denominator. We don't as a negative exponent. All right, I just keep forgetting to do it. To the following, okay. So the 9 comes down. 9 times 10 is 90 x to the 8. Okay. Now it's going to be 3 pi x squared. Oh, and actually, what I wrote was dx. These are the derivatives. This is the same as 2/3 4. So then our dy by dx down, that's going to be a negative 8/3. Negative 5th. And then let's not leave the exponent negative. So we're going to get 3x to the 5th. On top, we're going to have 8, and this is on by x squared negative 8/3x to the power of 8. Squared negative 8/3x to the 5th. I think we got all of that. Okay. Sum and difference rule. So the sum rule, the derivative of a sum is the sum of the derivatives. Again, the derivative of a sum is the sum of the derivatives. So if we take the derivative of something plus something else, we can essentially break it apart. It's kind of like distributing, but we're not really distributing. But the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. Derivatives. So we've gone through like several shortcuts. So all that stuff, what we were doing, the limit definition of the difference quotient for the derivative, these shortcuts just bypass all of that, right? So then for part A, we have d by dx, 5x cubed minus 7, right? So then that's going to be equal to, so for that first term, the 3 comes down, that becomes 15x squared. The derivative of a constant is 0, so we stop there. E, we have d by dx of 24x root of x plus 5/x, okay? So then this is going to be equal to, so the derivative of 24x is just 24. Now remember, square root of x is the same as x to the power of a half, so that 1/2 comes down, x to the power of a negative 1/2. And then now 5 over x is the same as 5 times x to the power of -1. So then that -1 comes down to 5x. Instead of to the -1, now it becomes -2 because -1 minus 1 is -2, right? So then let's just rewrite these without the negative exponents and without the radical, the rational exponents, right? So then ultimately, we can get this down to 24. So then that's 2 times the square root of x under the 1. We're subtracting that. Over x squared. Like, I have to wake up. I'm just waking up. I don't know. I just feel drained. Oh my gosh. Okay. So for part A, and the next one. 24 minus 1 over 2 root x minus 5x squared. I think we got all that. Check as an exercise, okay? You have the original, you can see the solution there. My recommendation is to take this original and work it yourself and see if you can same conclusion. Find the points on the graph of this function. This tangent line is horizontal, right? So remember, we said earlier that the derivative is the slope of the tangent line at a point. So if we want to find when the tangent line is horizontal, that means that the slope is going to be 0. So in other words, we need to points x values that make the derivative 0. Right. So we have this f of x equal -x cubed plus 6x squared, right? So if we're going to take the derivative, let's go ahead and take the derivative. So then f prime of x is going to be a -3x squared plus 12x, right? Then now if we want to find when the tangent line is horizontal, that means it's going to have a 0 slope. So we need to find those x values that make the derivative 0. So we're going to set this equal to 0 and solve. It looks like we can factor out a -3x on both terms, right? So if we factor out -3x, look at the x. The second one, it looks like we're left with what, 4. Just as a quick check, -3x times x is a -3x squared. X times a -4 is a positive 12x. Okay. Use the 0 factor property. We have 2 or more things that multiply to give us 0. We just basically set each thing to 0 and solve. So 3x, we're going to set that equal to 0, and we're also going to say x minus 4 equals 0. So from the first one, you divide both sides by -3, x equals 0, or x equals 4, right? So these are the x values where the graph of this function, where the slope of where the tangent line intersecting these points on the graph should have a horizontal, should be flat, right? Should be horizontal. So we just need to go back and find the corresponding y from the original. So then if we do when x is 0, the corresponding y is 0. When x is 4, we're going to have a -4 cubed plus 6 times 4 squared. -64. 4 times what? 16. 16 times 6 is 60. Is 32. it looks like the tangent line is going to be horizontal at the origin, 4, 32, provided we didn't make any calculation errors, you know, it should be good. And we could check this by like looking at the graph, you know. To go ahead and find the equation. Like, so we have the slope, right? If the tangent line is horizontal, that means the slope is 0. So we have our slope and we have a point for on each of these lines. So we could find the equation of those lines and graph all three. We can graph the original function and the two horizontal tangent lines. And you'll see, I guess I need to do it. I was avoiding it because I'm like being lazy. But we can do it. I mean, to save it, but for some reason it makes me losing it. Load and refresh. Horizontal line, that means we can just take the y value. So let's put the original first. Go to y equals. We have this negative x cubed, so x to the power of 3. Horizontal line, if it's back to the origin one, is y equals 32, right? Flat. These are fine, but our y values, we need to go to like maybe 40. Go up to 40. To 5 on the y-axis, right? So now if we look at the graph, is one of our horizontal lines. You see it, you know, it touches at the peak, and then the other horizontal line touches at the x-axis touches at that valley, and then the other horizontal line touches at the peak, right? So you can see the degrees. Is the slope of the tangent line to a curve, and the slope of a horizontal line is 0. Therefore, we wish to find all the points of the graph of f with the derivative of f equals 0. 0, and when x is 4, and then the corresponding y values were 0 and 32 respectively. And so they got the same number back. This is what we just showed on that calculator. X, to find the points on the graph. Find the points on the graph of this function at which the tangent line has a slope of 6. So in other words, if the tangent line has a slope of 6, that means we need to set the derivative equal to 6. So let's go ahead and find the derivative. So then f prime is going to be a negative 3x squared. 6 times 2 is 12x, right? Equals 6. So let's go ahead and set it equal to 0. We subtract 6 on both sides. So then we'll get negative 3x squared plus 12x minus 6 equals 0. At least a negative 3 from all terms. The x squared minus 4x I think we can factor this, right? Not in the traditional sense. We could try either the quadratic formula, square, nine and two. Yeah, I don't think it's quadratic formula. Quadratic formula is x equals the negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m. I know it's a little bit non-PC, but that's so. One of my students shared that with me like in the past, and it was instantly ingrained in my memory. So I like to pass it on. And you can obviously change the story or narrative, but that's the way he remembered it, and it just locked it into my mind. So, because it's like, to me, it's like watching a movie. It's like watching the movie Hangover. It's that formula, right? It's kind of interesting, but that's what you got to do. You got to find like memorable ways of getting into it with this information or whatever. Okay. I'm going to use my simplified form instead of the original. I could use that second line, but I just felt inclined to use the last line. The numbers look much more simple. And I think we'll get the same result. Negative b. So that's going to be what? 4 plus or minus 16 minus 4 times our a is 1 and our c is what, 2? All right. 16 minus 8 is 8. I'm just going to kind of continue up here. 8 is 2 root 2. So this is 4 plus or minus 2 root 2 over 2. Then that's going to be 2 plus or minus square root 2. These are the x's. We would have to go and find the corresponding y's. I'm going to stop here. I'll just highlight it. I just don't feel like using the calculator. But if this is the x's, right? We just plug them into the original to find the corresponding y. Okay. See the type notes. I'm going to piggyback on my type. So we already found f prime of x. All right. 6. All right, there's that one right there. All right. So we got 2 plus or minus root 2, right? He's into the original. It's 10 root 2. Exact results there. These are points where the slope of the tangent line is 6. Common forms of notation of the derivative of a function. We have y prime, we have f prime of x, the derivative of y with respect to x. You also might hear me say dy by dx, d by dx, or the derivative with respect to x of f of x, right? I don't know. I'm just sleepy. I usually try to do these presentations when I first wake up, so I'm not so drained. But for some reason, I guess I just didn't get good sleep. So we have the power rule for differentiation, the derivative with respect to x of a power function. Basically, that power comes down and we subtract 1 from the exponent. That's what this is saying. Constant is 0. The d by dx of 0, because that whole discussion comes out of a constant can be written in the form of, like, for instance, the number 2 is the same as 2 times x to the power of 0. But because the 0 function does not have a unique exponent, the zero function, like x equals 0, that can be written in the form of like 0 times x to the power of 0, which is equal to x to the power 0 times x to the power of 2. Like you can write 0 several different ways. So I don't know why this is mentioned it. I thought it would. Maybe it'll bring it up a little bit later. But well, I feel like 0 is not differentiable. Hopefully I'm not mixing it up. Maybe they didn't bring it up because it doesn't apply here, but I think that's what it is. I need to look that up. The times of function is the constant times the derivative. The derivative of a sum or difference is the sum or difference of the derivatives. That's not too terribly bad. On that note, we're going to end the session here. I got one beautiful mind to another. Enjoy the rest of your day. Okay, take care. Peace.